Okay, so good morning, everyone, and welcome to another edition of the University of Washington's Data-Driven Methods in Science and Engineering seminar. I'm very excited for our speaker today. So we have Dr. Beverley McKeon, who is the Theodore von Karman Professor of Aeronautics at the Graduate Aerospace Laboratories at Caltech and the Deputy Chair of Division of Engineering and Applied Science. So her research interests include the development of resolvent analysis for modeling turbulent flows, interdisciplinary approaches to manipulation of boundary layer flows using morphing surfaces, assimilation of experimental data for efficient low order flow modeling, and fundamental investigations of wall turbulence at high Reynolds number. She was the recipient of a Vannevar Bush Faculty Fellowship from the Department of Defense in 2017, the Presidential Early Career Award in 2009, and an NSF Career Award in 2008, and is a fellow of the American Physical Society and the American Institute of Aeronautics and Astronautics. She is the past editor-in-chief of Experimental Thermal and Fluid Science, and currently serves as an associate editor of Physical Review Fluids, as well as on the editorial boards of AIAA Journal and Experiments in Fluids. She's the chair and APS representative of the U.S. National Committee on Theoretical and Applied Mechanics. So I think that we're in for a very exciting talk today. So Dr. McKeon, I will hand it over to you.
Thank you very much, Jason, for the kind introduction. Some of that information actually turns out to be a little old. So I'm actually a co-lead editor of Physical Review Fluids right now. So I should have updated you, but there was no need to give all that information, but I appreciate the kind introduction. So thank you. And thank you also for the invitation to speak. So this is a really wonderful series bringing together a great array of topics and speakers. And so it's very nice to be able to speak here and to represent wall turbulence. So I was saying to the organizer at the beginning, I'm going to sort of subvert this a little bit and be very specific with what I mean by data in terms of data-driven. The title here is What's in a Mean, and I'll define what I mean by that. And we're working towards nonlinear models of wall turbulence. So the people who've been involved in the work that I'll show today primarily are Adi Sharma of the University of Southampton, a longtime collaborator, former students Ryan McMullen and Kevin Rosenberg, current student Ben Bartle, and a collaborator Xiaozhu Zhu, who's currently at Harvard University. And the funding is gratefully acknowledged. So why are we interested in turbulent flow? In a series like this, I want to just spend just a little bit of time talking about why we might be interested in modeling turbulence, and ultimately a goal is to control. So control flow to shape the future. There's sort of all sorts of terribly punny titles I could have here, you know, turbulence in turbulent times and all those sorts of things. But another student in the group put together this little box at the top here from a My Climate website when we went to a meeting, you know, in the before times, we went to a meeting in the UK, the Turbulence and Shear Flow Phenomena Symposium. And so that particular trip, LA to London, contributed 3 tons. 3.3 tons per person of carbon dioxide. Pre-pandemic, the average was something like 16 tons per person, and just above half that actually in Europe. If you're traveling on a commercial aircraft, something like 50% of the fuel burned is due to drag from turbulence. So that is to say, if the flow were not turbulence, there would be much less fuel burned. And so we can sort of join the dots in terms of fuel use and pollution. Now, what's going on if we look at this? Goodness, I can see this laser pointer is doing something funny to my screen. I'll take that off. If we look on the wing, say, or even on the fuselage of a commercial aircraft, and we look very close to the surface, in the region, the boundary layer between where the flow travels with the velocity of the aircraft and where it adjusts to the velocity of the quiescent air around, or the wind speed around the aircraft, there's a lot of activity. And so for aircraft of this scale, The boundary layer is turbulent for a good portion of wing and fuselage. And we'll spend a little more time with some of the details that you can see down here in this bottom panel. That's a representation from a turbulence simulation, just showing some of the structure, turbulent structure or coherent vorticity that you see in a turbulent boundary layer. So just flipping back to that, hopefully in this bottom panel, you can see that there's activity on a range of scales. And so let's just set the scene here a little bit in terms of that range of scales. So if we move from left to right in terms of Reynolds number, so this non-dimensional number that incorporates the velocity and the length scale and the kinematic viscosity. So if we increase Reynolds number, so for an aircraft at a constant altitude, you'd be increasing speed. Everything I'm going to talk about today is at 0 Mach number, incompressible flow, but the tools can be used for different conditions. So if we increase the Reynolds number, we go through a transition from laminar to turbulent. It's not a point in many flows, certainly not in the flows that I'm looking at. It's a sort of region of Reynolds number where the fluctuation level becomes much higher. There's a turbulent dissipation of energy, and there's an explosion of scales in the flow. So as we go left to right, if we increase Reynolds number, this is a wind tunnel facility in one of my labs, sadly idle right now because of the pandemic. Further out here is a pressurized pipe flow facility. That's actually me as a graduate student in the middle there. This is the super pipe at Princeton. And in terms of the overlap, you can see that that's just about touching to a transcontinental natural gas pipeline. It's close to commercial aircraft or an oil tanker. Then far out to the right in terms of the highest terrestrial Reynolds number would be, say, the atmospheric surface layer. And you can use that as a proxy for a very high Reynolds number boundary layer during near neutral thermal conditions. So the transition from stable to unstable flow. So this is a typical range for the laboratory. Our simulation techniques reach up into the regime that we can access for simple flows in the laboratory, in my laboratory, and certainly not quite up to the more specialized flows. Excuse me. But if you want to get higher than that, you need to have some kind of modeling in place. And so one of those techniques is large eddy simulation, which resolves the large eddies and models the small ones. And we could continue down the sequence here to say Rand's equations, Reynolds average Navier-Stokes simulations, which have more modeling and less resolution. In fact, only the mean temporal average is simulated. So why this gap? Well, if we look at the range of scales that's observed in a wind tunnel, in fact, this wind tunnel, a flat plate experiment there, we'll find that the longest coherent structure, so the longest region that we need to be able to capture in any observation of the flow or simulation is something like 2 basketballs in length. The thickness of the boundary layer, that region of adjustment from the surface of the wing to the quiescent air, or in this case from the flat plate at 0 velocity to a wind flow, a wind speed over the top, is something like the diameter of a golf ball. And the smallest scale that you need to resolve is about the diameter of a red blood cell. So that's not quite to scale, but that's a reasonably generic wind tunnel facility. If we look now at what used to be the longest oil tanker in the world, the largest oil tanker in this picture, I mean, picture a generic big oil tanker. If you stand that on its end, it's about the height of the Empire State Building. This long coherence, the 2 basketball length, is about the height of a 3-story building. Whoops, 3-story building. The boundary layer thickness at the end of the boat, of the ship, is about the height of me, 5'10", reaching up as high as I can. And the smaller scale then is a fraction of the diameter of a human hair. So the difference between the largest and the smallest scales with Reynolds number in a very unfavorable way. So hopefully this motivates needing to do some kind of modeling, and also motivates the fact that there will be big data associated with some of these flows, but that it's hard to obtain that given the complexity of some of these engineering flows. So what I want to focus on today is given all these types of data that I'll run through in a minute, how far can we get with sort of the minimal data input? So here's a schematic of a flow over a flat plate, a turbulent flow. And if I were to visualize this, this is from the work of Gad el-Haq, so this is a laser-induced fluorescence. So the yellowy orange part is sort of the edge of the boundary layer, or sorry, the yellowy orange is contained within the boundary layer, and the black is a free stream over the top. You can see that there's a very complicated edge or shape to this, that if I were to have a position a probe out here, then it would intermittently sample turbulence and non-turbulent fluid as this convected downstream. This is a schematic representation of what the temporal average of the streamwise velocity would look like at a given station. And so the reason to compare and contrast those two is that the mean profile is smooth, continuous, and it is definitely an average representation of something much more complex. So we're going to work with the information that's bound up in the mean and see which of these other pieces of data, observations, can be modeled using information contained in the mean. So in these images here, you can see both another visualization with bubbles, hydrogen bubbles. This is a particle image velocimetry field in the streamwise wall normal plane. Here is one in the wall parallel plane, and these are the sort of two basketball length coherent structures in the streamwise sense. And then this is the full simulation. So this is a direct numerical simulation, visualizing here connected vorticity. So something related to the velocity gradient tensor that identifies structure that has vorticity and is connected in a spatial sense. So all of these things could contribute to our observations. And we have many of these in the community. I wanted to just recap quickly a subset of approaches, or data-driven approaches first, to modeling this flow, or these types of flow. There's a very large literature on these data-driven representations and modeling for applied to fluid flows and turbulent flows in particular. The ones I want to draw attention to here are dynamic mode decomposition, or DMD. And so that's a linear, trying to find the operator that gives a linear advance between observations of a flow. And that has connections in a theoretical way to Koopman mode analysis. And I'm not going to go into that here. But basically that's finding a representation that captures energy preferentially or in a ranked way at a given frequency, Perhaps more familiar generally is proper orthogonal decomposition, also known as principal component analysis or Kahunen-Lev analysis. We'll call that POD here. And so that again is looking at the energy in the flow and trying to decompose that into a basis that optimally represents the energy in the flow, gives you a spatial representation with time varying coefficients. That was originally conceived by or applied in the fluids world by Lumley. And to some degree, the implementation has been limited by the types of data we've been able to obtain for many years. The spatio-temporal part of that was hard to do. Recent work by the group of Colonius at Caltech, so Town et al., actually implemented this in a spectral way, so spectral POD or SPOD. And that allows you then to get a spatial mode that oscillates at a single frequency. So here's a little comparison of POD modes on the left. This is flow over this particular body that you see here with this shape in gray. So here are the dominant and the secondary modes from POD and also from DMD. So there's some similarities and some differences. There's an increasing focus, and that's what I'm going to draw on here, on equation-driven approaches. And obviously a question there is, what are the links between the equation-driven and the data-driven models? And we'll come back to that. I'll just say that the summary of these techniques as applied to fluids. A recent one was given by Tyra et al., a review paper from 2017 in AIAA Journal. So let's get to the meat of the approach. So this is an equation-driven method. I want to speak to you about resolvent modeling. Here's a representation up at the top there of what we know as the Reynolds decomposition. So if I have an instantaneous field, so this should have dependence on space and time, I can divide that into something that is a temporal mean in this instance, and something that has both spatial and temporal dependence, right? So a fluctuation, a mean in blue and a fluctuation here in black. And I'm not going to go through the equations per se. I want to give this at a higher level. But if I took the equations of motion, the Navier-Stokes equations, I could write them in this form. So I could write them in terms of a linear operator and a nonlinear term, a quadratic nonlinearity in the Navier-Stokes equations. And I could schematically represent them like this, and even conceptually represent them like this. I could think about the quadratic nonlinearity as providing a forcing to the linear dynamics in a way that this is a closed loop. And the thing to draw out here is that those linear dynamics need as an input the turbulent mean in this formulation. So I'll try and stick to this color coding throughout the talk. So the green will correspond to the linear dynamics, which are, that operator is known as the resolvent, hence the name. The red will correspond to nonlinear forcing or something on the nonlinear side, and the blue will correspond to the turbulent mean. Now, that's the particular picture that we have been focusing on since 2010. But the picture or parts of the picture have been around for a long time and have a long history, which I'm trying to sketch out here. This is sort of the historical piece. There's a lot of ongoing work now, and I just will not be able to reference all of that. So conceptually, the interesting things are, if I were to remove that nonlinear term at the top, then this could be considered as a linearized stability analysis, where the linearization is about the mean. And there's some implication that the mean profile or mean field gives rise to a neutrally stable operator. So that was the proposal of Malkus. That turns out not to be true for these flows close to a wall. It is true for some other flows. Related to this setup is an initial value problem, or the transient growth problem. And then if I were to consider, so that's the initial value problem. If I were to consider an input continuous forcing, then that work has been advanced by Farrell and Ioannou in '93. Jovanovic and Bamier really set the foundation for thinking about this transfer function approach, this input-output idea. So if I have an input F, how do I maximize the output associated with that input? And then our work has closed this loop, if you like, put back the nonlinear forcing to say, let's not try and work out what gives us the largest output, but let's see if we can't close this somehow using what we know to be the forcing. A lot of subsequent work that develops on this, trying to shape the right-hand side, this forcing term here. And there's a very nice review paper on these input-output techniques from Mihailo Jovanovic in the annual review of fluid mechanics last year. I'm going to develop the approach that we laid out in McKeon and Sharma in 2010. And so if we actually write the Navier-Stokes equations in this transfer function form, the green part here, once we have Fourier transformed in homogeneous direction, so here let's consider a channel flow, so we can Fourier transform in the streamwise and the spanwise directions and in time. So I'll parameterize by this bold K. So the green part then is that for every K, we can write the response U in terms of the resolvent acting on the forcing. The red part then is that the forcing must be given by the nonlinear interaction, quadratic interaction of the U's at all other K's. So K prime here. And if you put those together, here's the full expression of this setup, full expression of the Navier-Stokes, so no modeling in there per se. Haven't got rid of the closure problem. We've just reformulated it in a particular way. Now, how do we sort of connect with these ideas of getting the most energetic or the most amplified modes in a basis? Very similar to the concept behind POD or even DMD. So how do we get a ranked representation of both disturbances, F, and responses, U, that might be important for these kind of flows? And so we can do the Schmidt decomposition, the singular value decomposition of the resolvent, H, for a given K. And so that's shown here in the green box. So here, sigma is the singular value or the gain. The SVD going down in the basis representation is described in terms of J. So sigma at K for the jth version is the jth gain, and these are ranked in the SVD. So the sigma 1 is much higher than sigma 2, or is higher than sigma 2. So those are the gains. These are the response modes that are excited by these phi modes over here. So we can decompose H into two bases, a response basis and a forcing basis, and we get the gain between them, and the SVD gives them in a ranked sense. So if we consider this in a discrete setting, we could now write every U in terms of this basis set. So we can write U in terms of the psi functions. There'll be sigma times however much times this chi function, and the chi is how much of each phi function is present in the data or is needed to close this loop. And I put an asterisk here to say for these, especially for these extremely multi-scale, very turbulent flows, it's also appropriate to consider the stochastic problem. So at that point, we're sort of getting away from really thinking about individual modes and thinking about this as a sum, thinking about this in terms of an integral representation instead. And I'll come back to that too. But the summary of this slide then is, if I buy this representation, if I want to follow this route, the things that I need to know are the mean profile. So that's an input as written here. And then if I can learn these chi functions or the weightings on each of these basis functions, I can actually close this loop, or at least conceptually close this loop. Let me say a little bit about why we might have this particular basis and sort of what's underlying it. So the Navier-Stokes, the linearized Navier-Stokes operator, the resolvent, is a non-normal operator. And so just to recap what that means, here's a couple of very simple examples. So S has this form, P has this form, so we've added in the non-normality here. If I were to look at the spectrum, I would find in both cases I have the eigenspectrum, I have the same eigenvalues. And if you were to perturb these flows, on the top case for S, in all directions, the eigenvalues would move in a proportional way to the disturbance. For the non-normal case, that's not true. And you can get very large disturbances or very large disturbance amplification. And it doesn't necessarily line up with the frequencies associated with the eigenvalues. And so that's an influence of non-normality that was laid out in Trefethen et al. In 1993. So that's underlying this. And what's really interesting here, so this right column is the value of the perturbation that would move the eigenvalue out to the zero axis and move to neutrally stable. And we see here again that those peaks line up with the eigenvalues. Down here, we see that they don't. So the peak is in blue, is at a different location to where the eigenvalue sits. And this property that we're looking at on the axis, on the real zero axis right here, is the resolvent norm, and also the first singular value, so the maximum amplification that can be obtained for the perturbation of this particular operator. So in the context of what I was saying before, we are looking to find perturbations that move us to this axis right here to give us neutrally stable disturbances or velocity modes, and therefore things that we would expect to observe in a statistically significant way, or in the statistics of a flow, but basically not transient. So not things that decay and not things that exponentially grow. Last thing for this slide is to say that there's, in a technique sense, there's been really significant progress made very recently in computing the resolvent. So that can be, for the one-dimensional case that I started talking about, that's trivial, can be done in MATLAB on a laptop. For the two-dimensional cases or more, actually calculating the resolvent is computationally intensive, but there's some nice work from Ribeiro et al. That for the 2D case uses randomized linear algebra techniques to do that. Okay, so let's just return to this idea of these different modal approaches. And I should have said at the time, I restricted myself to this particular representations because of the connections to the resolvent analysis. Clearly, there are many other nonlinear techniques that could be used for modeling of the dynamics. So this orange box at the bottom is the key piece here. So the data-driven S-pod modes, spectral POD modes, and the resolvent modes can be shown by Town et al., to be identical for uncorrelated or white forcing. So that is to say, if we put no preferential shaping on the forcing or on that nonlinear interaction, then what you get from the equation-driven analysis and what you get from the data-driven analysis, those modes will be identical. So the S-pod modes are optimal in terms of describing the data. The resolvent modes are connected directly to the equations of motion and will be suboptimal in terms of describing the data, but are still useful. So about halfway through, so let me just give you some examples and build up this picture of working from the mean and using different pieces of data to build some model representations of turbulence close to a wall. So the first one is working from the velocity spectrum, or actually 4 velocity spectra in turbulent channel flow. So here's the image I've seen a couple of times of structure in a channel flow. So this is from direct numerical simulations, and we look over this range of Reynolds number. So RE tau is a Reynolds number defined, a typical one defined for wall turbulence. Just to give you a sense, in the atmospheric surface layer, it's something like 10 to the 5. In a large wind tunnel, it's something like 10 to the 4, several 10 to the 4s. So this green one is about the state-of-the-art simulation in terms of the Reynolds number. So Hoyos and Jimenez and Lozano, Duran and Jimenez kindly shared some of these results that I'll show you. So the data that we're going to work with here, a sequence of velocity field time snapshots has been used to obtain the power spectra of the velocity fluctuations. So streamwise, wall normal, and spanwise variances here, and the Reynolds stress, so the cross variance here, the UV, and the bar is the time average. So here are the dimensions for each of those. So the data sets here would be nx by ny by nz, that's the field, by nt, that's the number of time snapshots. And in terms of the spectra, that reduces to nkx, nkz times the number of points in y times the number of velocity components that we're looking at, so that's 4. Our resolvent model will look quite similar, except that we're going to look, so we've got nkx, nkz, and ny. Nc is the number of wave speeds that we'll emit, so that's in the 1D case, that's the frequency divided by the streamwise wave number, that's the convection velocity. And then this n modes refers to how far down the SVD we're going to go, so how many J's we're going to look at. And to give you some sense for the degrees of freedom here, for the DNS data, if you put those numbers in, you have something like 10 to the 13. The model that I'm going to show you is a significant reduction, so like 10 to the 7. And actually, if I look per wave number pair, our model requires 0.01% of the number of degrees of freedom required to construct the field, required in the DNS to represent the field. So why is that? Here are those numbers again, just put up at the top. So let's take a look. So first of all, we're going to reduce the number of Y points. We reduce the number of wave numbers that we take a look at, and the number of, here we are, the number of frequencies. And we use a 6-mode representation here. So why can we do this subsampling? Well, we know observationally that if we look at the mode shapes and we increase the wave speed, or in this instance, it's written as increase the Y critical. Don't need to really introduce that here, but it's related to the convection velocity. You can see that the mode shapes change, but they change in a pretty benign way. And in fact, there is a semi-analytical form that Scott Dawson published when he was a postdoc with me that shows that there's real connection to some of the asymptotic results from the stability literature. And in fact, the first mode shapes are well described by just a Gaussian in Y with a pi phase change. So there's a benign change in the shapes, and there's actually also shown by these two plots, self-similarity that comes from the self-similarity of the mean profile. So that is to say that turbulent mean U, we know how that scales with distance from the wall and with Reynolds number. And there are distinct scaling regions, and that's also impressed onto these mode shapes. So I can collapse these modes on the left to the ones on the right using the scalings that come from the mean profile. So that all helps. The other things to note, there are some other sort of tricks of the trade, if you like, or Sommerfeld and Squire mode. So we have to be a little careful with how we construct the resolvent so that we don't omit a homogeneous solution as well as a forced solution. So I won't go into much detail, but basically the blue here is the forced solution. The red is the homogeneous solution, and they destructively interfere. So the net mode is this black one, and you can see that for two different cases here. So there's some data-driven inspiration, if you like, or some domain knowledge that tells us that the scaling is benign enough that we should be able to do this subsampling. But this idea of having 6 modes in the SVD, that speaks to the effectiveness of the resolvent basis. So what do we do? Well, the energy in the spectra, parameterized as a function of y and as a function of kx, kz, and this wave speed, so omega on kx, we can write that in terms of the real part of the trace of arx. So the r, in this case, I've expanded it for uu. And so A is all determined from the resolvent. So with knowledge of just the mean, we can determine both the sigmas and the mode shapes. And then in X are the chi's. So this is what we need to find if we want to reconstruct E to represent what we see in the data. So here's the expression of what we actually do in terms of an optimization. So we try to minimize the difference between our resolvent mode representation and the DNS. So to cut to the chase, here is a representation of our first mode. It's a little bit complicated because we're allowed to have interactions between the modes in the SVD. So the J and the J+1th mode can interact for a fixed K. But here's a representation of part of what is in that X matrix, so part of the weights that we determine. And you can see here we've got a clustering up here. This is for the Squire modes, this is for the Sommerfeld modes. And we can see now where those sit in terms of the wavelengths in the spanwise and streamwise direction. But let's take a look at marker size proportional to the magnitude, that's right. Let's take a look to see now how well we do with that reconstruction. So on the left, we've got the lines are the DNS result, and the colored isocontours are the results from our resolvent model. We're showing here the streamwise, wall normal, spanwise, and Reynolds stress spectra. So visually they look very good. If we integrate, over here, the two solid lines are the comparison. So the black, again, is the resolvent, and black is the DNS, and the blue is our resolvent model. If we hadn't accounted for this or Sommerfeld mode, square mode separation, our optimization would have given us the dashed line. So you can see why we do that. It helps the performance. So things look pretty good. We trained on, if you like, we learned from those 4 spectra on the previous slide, but how well do we do in terms of things that we didn't, information that we didn't have coming in? So we had no information on the distribution in frequency, and showing here are the other 2-dimensional plot. So this is the distribution for a fixed Y, the energy in terms of the frequency and the streamwise wave number. And so you can see that the energy actually sits in the right place. You can see the striations that are to do with us doing the subsampling, but it seems to be very encouraging. And the same is true for the frequency KZ spectrum, which again, we didn't have access to these, so we didn't use these in the optimization that I showed you on the previous slide. We changed Reynolds number here just so that we could get our own statistics of the forcing now. Now it says GV and G eta because we ran the code in velocity vorticity form. But basically this is the spectrum of the forcing reconstructed from our resolvent model, that's in blue. And the lines are the ones that are obtained from our lower Reynolds number DNS. And so once again, you can see that the effect of reducing the number of degrees of freedom is present, but the forcing lives in the right space. So we have the kernel of a representation of what modes are important. And we can learn from that. So here's a representation of the mean profile versus the log of the distance from the wall. And here are the 3 Reynolds numbers that are shown on the right. And there are different regions of collapse. So you can see the 3 lie on top of each other here, very close to the wall. And so that's percolating through the resolvent to show us that the weight of we're looking now at the weight of the Orr-Sommerfeld and the square modes relative to each other. Our similarity scaling tells us that shouldn't be a function of Reynolds number. And indeed, to the left of this dashed, this gray line, so that's corresponding to the location of this gray line, you can see collapse, but more or less, between the different Reynolds numbers. Similarly, if we go out and we look at a velocity deficit, so that's the difference between the highest speed, mean speed in the flow, and the local speed. Out here, there's collapse between the Reynolds numbers. Scaling analysis tells us that this ratio of weight should depend on Reynolds number. And in fact, if we look at the unscaled versions, there's sort of a mess. If we look at this scaled version, again, to the left of this gray line, we have collapse between Reynolds numbers. So that is to say that by starting from the mean, doing our data-driven optimization, we now have information about weights on this data basis that we didn't have before, and scaling laws. The last piece to show you here is that between those 2 gray boxes, there's a region known as the logarithmic region, or the overlap region, or the inertial region. That has a very specific scaling. It leads to a geometric self-similarity, dictates a lot of the behavior actually of turbulent flow close to a wall, or significant dynamics sit there. And in that region, you find that the ratio of these weights should be proportional to this distance from the wall, scaled in viscous units, Y plus. And so what we found there that we didn't know before is that this ratio of weights should be linear with Y. And in fact, that works for 4 different self-similar hierarchies in this flow. So one can go and plot what those hierarchies look like. And here's a planar and a 3D view. And hopefully you can see that there are some similarities here. I'm not going to go into much detail on that. And there's really, you shouldn't take anything from this comparison more than visually things look kind of the same. But we have ways to do that in a more rigorous comparison. So again, the data here, or a limited set of data, starting with the mean and including the spectra, has led us to the weights on our resolvent basis. Okay, shifting gears for just the final few minutes. I want to talk to you about some work that Ben Barthel has been doing in my group, and we're switching to Taylor-Couette flow. So two concentric cylinders with a gap between them. So the gap here is the difference between the outer cylinder diameter and the inner cylinder diameter. And in the case that we're going to look at, we'll have the inner cylinder rotating. So of course you could, this is a very, very rich dynamical system because you can have both inner and outer rotating, you can have them co-rotating or counter-rotating. So it's been studied in a lot of detail. If you put reflective particles into the flow, you see these very, very distinct structures as you increase the speed above the critical Reynolds number. So we're going to look at a particular ratio of inner to outer diameter. This is a picture from Coles, who was a luminary of Gauss-it, Caltech, who did a lot of work in wall turbulence and really documented some of what was going on in Taylor-Couette flow. So this isn't quite the regime we're going to look at, but I want you to see here that there are bands, right? So there's a distinct wave length in the axial direction, and you can see some wave superimposed on that. So as you go up in Reynolds number, first of all, you get this generation of these Taylor rolls or Taylor vortices, and then you get a superposition of a waviness on top of that with a restricted wave number. So we're going to deal actually with the Taylor vortex regime here and use the same machinery, but now we're going to include another constraint. So rather than just trying to match what's going on in terms of the spectrum, the output here, we're also going to require that our modal representation satisfies this nonlinear term to feed back and drive the linear dynamics. And we're going to require that the self-interaction is enough to sustain the turbulent mean that we started with. So once again, we're learning the chi's and we're making sure now that we're consistent with the mean profile. So we do that in a similar way. So we're running this as an optimization. So now we want to try to include a constraint that weights quite low, in quite a small way, the idea that we need to have the right forcing to sustain the mean that we started with, but then also make sure that the velocity field that we have over all k is correct to sustain through the nonlinear term that velocity field. So two parts, we want to close this loop, and then we also want to make sure that our solution satisfies this turbulent mean. So it turns out that satisfying the mean is sort of a least squares fit, and if you weight that too much, you just get the trivial solution. So you don't need to put a very high weighting on this, but it turns out to be not super sensitive to the value of A. So here's the solution. So this looks probably terrible. There's a lot of information to convey here. For each of the wave numbers, so this is the fundamental, so these are the harmonics of that fundamental. We're showing here in red the sigma j's. So as you go up in the SVD for this mode and the resolvent itself, this is the roll off of the singular values. And so this is sort of at the heart of why the resolvent approach is effective. And that is that there's a severe roll off in the singular values. So that is to say that there are, there's a band of disturbances that are amplified, and there's a whole load of modes that are either in the null space or very close. They're just not amplified. On the left-hand side, we have both the chi's and the sigma chi's. So the chi's are the actual weights on the forcing, and the sigma chi is clearly the product of the gain and the forcing. But this is very important because in terms of the roll-off of the blue of the chi's, you can see that there's a couple here that are energetic or large, and then again you roll off very quickly. So in terms of the weights, it doesn't seem like these modes are very important, but of course what actually counts is what you see, I'm sorry, the other way around. This is in the velocity field. But what you actually need to sustain this process, you have to include all of these modes to get this nonlinear closure. And so there's a lot of information on here, but this is the equivalent of our blob plot from the channel in terms of which modes do we retain in our model. Here's the reconstruction of the velocity field for 3 Reynolds numbers. We're looking at u theta, so that's the azimuthal velocity, and then the azimuthal vorticity on the right, model on the top, DNS on the bottom. So visually, hopefully you'll agree that's sort of indistinguishable. Interestingly, if we go back and check what is the agreement between the model and the DNS now, red, blue, and black here are the increasing Reynolds numbers. And the lines and circles are I'll come back to that, a primary and forced response, and the squares are the DNS. So over here, everything sits on top of each other. So that's not, I mean, it's good, but it's not so interesting. But over here, there's a distinction between the DNS, the squares, and the overlap of the primary response. So that's the left-hand side of U equals HF, and the circles, that's the nonlinear interaction of all the other modes in the model. So what we find is that we've closed our model, and those things agree, but it's a little bit different from the DNS. And that makes sense because the DNS was performed in a finite domain, as a non-periodic domain. So we actually seem to have found a solution that's not quite what was present in the DNS. And this is a feature of Taylor-Couette flow non-uniqueness of solutions. So that's something that we need to explore some more. But there's a reason basically to see this. And you only see this difference at high K. So this is for K, 8 times the fundamental. Quickly, what else can we learn now from the model data, just as we learned about the scaling of the weights from in the channel flow? Here we can look at the nonlinear interactions. So that quadratic term is constrained. If we want to see a response at K1, we need to consider K2 and K3, where K3 is K1 minus K2. So there's a pretty tight constraint here in terms of that nonlinear or resonant interaction. And so I won't have time to go into this very much, but Ben did some really nice work identifying the difference between a lower Reynolds number, but still supercritical Reynolds number, in which a weakly nonlinear analysis is kind of appropriate. So what are we showing here? We're showing which, for this K1, what are the contributions of the different K2 and K3 pairs that could add up to this 4 value. And so over here, you see that we've got 1 interacting with 3, so 1 plus 3 and 2 plus 2. And if we go up to Reynolds number of 400, we now have 2 different branches of this. So telling us we've got to be thinking about both the additive and the difference interactions. So that is to say, if we want to get to 4, we're going to need 5 minus 1 and 3 plus 1. Okay, I won't have time to go into that. Final thing to introduce here, something I'm really excited about. I would love for Benjamin Herman to be able to present this very soon. In fact, he will be at upcoming conferences, and he spoke about it at the APS DFT. So thus far, we've talked about actually implementing, or behind the scenes, we've actually done the operations to determine the resolvent and the singular value decomposition. Benjamin's work here, here's a summary image from it, is focused on determining the resolvent only from data. So without having to do that, construct that operator, the resolvent, and there's an inversion in there that's expensive. So the idea here is to use a DMD type approach. So we get a data-driven eigen decomposition. So he puts in some initial conditions. This is for a channel flow. And you're able then to reconstruct enough of the eigen spectrum that you get the pseudo-spectral information that gives you the gains and gives you the modes down here. So you approximate the resolvent. This is subjected to the same limitations that DMD would be and the same opportunities for the different variants of DMD. I think the main takeaway here is that the resolvent modes reflect what data you put at input. And so, for example, you can see in all of this column, that you get a very different result if you look at a localized impulse than if you look at a distributed input. So again, I won't have time to spend very long on that one, but I'll close now by saying, again, apologizing for subverting the idea of data-driven. So I've put this into a very, very specific box of saying the data that I want to start with is the mean flow. And I showed you some examples where we used spectra from the channel to get weights on our resolvent basis. Now, the power spectra gives you the magnitude of the weights, but it doesn't give you the phase. And so there's some other work that was referenced on earlier slides by Town et al. And also by Jovanovic, Zer et al. That looks at ways to correctly get effectively the complex weights. And so you can do that in various different ways, but that's effectively matching the correlations and not just the spectra. But anyway, that deals with the green part here. What I was just talking about deals with sort of all three, right? So we've got, in what I was talking about in Taylor-Coët flow, we had a sanity check to make sure that our solution was consistent with the turbulent mean. We got the linear reconstruction, and that linear reconstruction was consistent with the nonlinear term. So that's the color coding up here. I gave you a hint about the data-driven resolvent. So work ongoing to try to get away from the operator part of this and really get this basis that has a root in the equations of motion from data. And of course, the big picture, we have some work towards this, but at low Reynolds number, was to say, well, what if we don't know the turbulent mean at all? So one can do that from the Rand's equations, one could do that from experimental observations that are assimilated into a mean. But that's really the idea behind what we've been looking at. So data-driven in a very specific way. So with that in mind, I will close. I see 9:55, and I'll be very happy to take any questions.
Thank you very much, Dr. McKeon. That was a very interesting and just a great talk. Thank you. I'll open the floor to questions now. If anybody would like to ask questions, we still have a little bit of time. You can either type them into the chat, or I believe there's the opportunity to unmute yourself as well if you'd like to just ask directly. Dr. McKeon, I think you explained things so perfectly that no one has any questions.
Oh, that's one of the interpretations, right? Okay, well, I'm happy to hang around a little longer if anyone wants to speak after the fact, but thank you for your attention and thank you for the opportunity. I really appreciate the chance to speak and to subvert your series.
Thank you very much for joining us today. We really appreciate having you on.